Hello, my name is Ayush Kumar. Welcome back to my channel. So today we are going to talk about digital design and computer organization, in which we have taken a research paper which goes by the name "Ideas for Improving the Digital Design Lab." Let's get started. So this research paper basically explores the innovative approaches to optimize digital design workflows within the digital design lab. So we have the abstract. Now, common inclusion, traditional experiments, HDL integration, proposed solution, and HDL tool limitations. So first, in common inclusion, the digital design labs are a core of part of undergraduates program in electrical electronics and computer engineering. So traditional experiments, students typically build combination and sequential circuits using TTL integrated circuits like gates and flip-flops. So in the next, we have HDL integration, in which some autonomous institutions have included hardware description languages like HDL in the syllabus. But these tools comes with challenges, which we are going to discuss in the further part of the video. Next, we have a few proposed solutions in which the paper proposes using high-level language such as C or Python for digital design and simulation experiments. HDL tool limitation. HDL tools have a steep learning curve and are costly, making them hard to integrate into introductory digital labs. So I'll give you a small introduction of the whole thing. So digital logic design is a core subject in electronics and computer engineering UG programs. Typically accompanied by a lab course which might be integrated or external. And in this, basically, what the students will do is they basically going to be building a few combination and sequential circuits using TTL integrated circuits, which they'll be using tools like SDL and VHDL and Verilog, which are very useful in the industry, which are going to make them go head on with the industry things. And moreover, we have this paper suggested that use of programming languages like Python or C, which will be more efficient to operate than going for the some assembly languages, uh, because this higher level languages offer a simpler, more complex, flexible approaches that retains focus on circuit design, verification, and testing. We have done a small research survey about this. We have few similar papers on this thing and a few books in which S. Partiker, uh, which goes by the name Verilog SDL, a guide to digital design and synthesis. So basically, this thing highlights the importance of hardware description languages like HDLs, Verilog, the integration of HDL in the UG programs, challenging due to steep curves, which I have said earlier. And next we have the digital system engineering. This test basically shows the digital design and verification and at that period, which basically covers the digital systems beyond logical gates and is a key reference for verification and testing using software. And next we have Zhang et al. This paper basically focuses on FPGA in the teaching digital logic due to complexity and excessive capabilities for introductory level labs. It provides context for the paper's focus on simpler tools. So there'll be mainly two research areas which we would be exploring, which is design verification and testing, and another one is simulation tools for digital curves and circuits. So this area covers the verification of digital circuits and detection, validation, etc. And the second one goes with the deployment of simulation tools that help students learn digital design without physical labs, Python, and circuit design. So next we have the emerging trends. So this is basically there are three things in this, which is simplified tools, online and remote learning tools, and a few design verification and validation, which is going to basically help the students. So in simplified tools, we have a few higher level languages like Python or C, which basically used to simulate the logical gates in much easier way uh, than using assembly level language, which earlier students used to do, and it used to be very hard to operate. So this basically shift the student to focus on a more logical design process rather than managing complex hardware or tool environment. Next, we have a few online and remote learning tools such as Circuitverse, uh, QCSS Studio are becoming like very popular, which basically use simulates to get a proper understanding for the students. And next, we have design verification and validation, which basically goes into testing in lab exercises and encouraging students to think beyond just design and considering fault detection, debugging, validation process. These trends align with the industry practices, ensuring the student gain value practice skills. We need a few improvements in the whole thing. Like we have a few challenges like HDL tools and FPGA based lab present high barriers to entry with steep learning curves and significant licensing cost also. Improvements, the people suggest using simpler languages like C for digital simulation, offering an accessible alternative that focuses on understanding core design principle without the need for complex tools. Next, we have online lab accessibility. Now, traditional labs were disrupted during the pandemic era where many students could not access the physical labs. So, the improvement over here is like we using homegrown simulation programs, allowing students to continue their learning remotely, ensuring flexibility in how digital design labs are conducted rather than an ideal lab approach. Next, we have an architectural model for it, which basically contains of combinational circuit design, sequential circuit design, the runoff map, and testing and verification. In the architecture model, the main thing is again based on the use of simple programming language like Python or C to stimulate and verify digital logical design. So, in combinational circuits, using programming language to write and simulate Boolean expression for combinational circuits, example pull adders, comparators, etc. And next, we have sequential circuit design, in which using Python-based tools to simulate synchronous counters and other sequential circuits. In Karloff map, we have using simple Boolean expression using custom built tools. For the testing and verification part, encouraging students to use and talk about more defect detection such as stuck at faults and system verification in both simulation as well as hardware methodology. So in Python-based tools for combination circuits, a Python tool is provided to go with comparators and multiplexers, and this can use to basically generate the truth table and Boolean expression and vice versa. Because Python is again a very good stepping stone because it has many functionalities and many uh, libraries which you can use and create things and learn things. And we are if we use the same thing in the sequential circuit, then we have simple file formats are used to define flip-flops, state transition, and Boolean expression for the input, minimization and testing. The tool supports generation of Karnaugh map, which includes the students to verify the design. So if there are any faults in the system, they can easily go because they are going for testing. So that will basically help them in potential defects such as stuck at faults and integrating into the experiment to increase system level thinking. Real-time simulation, the use of Python enables real-time simulation of logic gates, making it easier for students to test their design across various inputs. Next, we have the whole result of the whole thing. So currently, we have a metric system which is design project completion time. The current status of it is 15% increase, which is again not good. Proposed model will increase the whole completion time by 10%, which is a huge thing because as much as they lower the time, it will be way better for the students because one, the time consumption is low. Second, they'll understand it in a way faster because it is again a high level language. Next, we have resource utilization efficiency. In the baseline model, we have 80% use of the thing, and in proposed model which will be 95%, which is again a 15% increase from the previous thing, which is again a good thing for the student. Next, we have design quality minor issues. In the baseline model, we have a few minor issues uh, which again would lead to more complexion, and in proposed model we have a significant improvements in the minor issues, which again is going to totally overlap the baseline model, which will again help students in a way better way, and students would be grateful for that. And next, we have the conclusion and the future work. So the whole paper basically summarizes on the use of more of like to get away from the traditional approach of the labs to a more higher standard approach of the lab. So this paper concludes by integrating simple programming language like Python and C into the digital logic design labs to improve the learning experience. It eliminates the high cost and complexity, which again, like if you're using a HDL, you would require the licensing, and if you use a FPGA tools, again you will be needing for the licensing and everything, and it is way more complex to operate than what we ideally will be using Python or C, which again focusing on design verification and testing skills will help the students to learn more. The approach is particularly valuable for remote learning environments where physical labs is limited. The proposed tool encourages creativity, system level thinking, deeper understanding of digital, making the lab experience more engaging and educationally valuable. So that's it for the video. I hope you like the video. Um, Make sure you like the video. Thank you.
I had all and then most of you, some and now